warm. In this session, we will look at Avl trees. So, what is an Avl tree? Avl tree is a binary search tree with a condition that each node's balancing factor should not be anything other than -1, 0, or 1. So, what is balancing factor? Balancing factor is the difference between the heights of left subtree and right subtree. So how do we calculate balancing factor and what makes a valid Avl tree is the question. So to understand, let us have a binary search tree. So I have something like this: 5, 4 and 9. Balancing factor of 4 and 9 are 0. For 5 the balancing factor will be 0 again. So this part has 1 edge and the height is 1, and right subtree is 1 minus 1 0. So what if the structure is something like 5 4 2 9? So here this is going to be 0, this is going to be 0, this is 1 and this is 1. So put in simple words, we just need to calculate the maximum number of edges you have in the left subtree to reach a leaf minus the maximum number of edges you have to reach a leaf in the right subtree makes the values, and this difference between them gives us the balancing factor. So let us take one more example: 5 4 3 1 here and 9. So here the balancing factor of 5 is 2. What if I have something like 5 4 8 7 9 10? So here the balancing factor of 5 is 1 minus 3 minus 2. So now these are the nodes that comprise the Avl tree property. So when we have a node that compromises the balancing factor, how are we going to reorganize the nodes in the tree so that the Avl tree property is met? So this is going to be the topic. So let us start creating an Avl tree for the given set of values 1 2 3 4 5 9 8 7 and 6. So before getting into creation of Avl tree, we just need to know what is called as a rotation. Rotation is the process of reorganizing the values or the reorganizing the nodes. So for example, if I have a scenario like this: 5 6 and 7, on insertion of 7 to this existing 5 6 binary tree compromises my Avl tree property at node 5, right? So what is the scenario here? I am inserting into the right subtree of right child. So now what action will make this a valid binary search tree and in turn a valid Avl tree? So a rotation here bringing down 5 and making 6 as root achieves this. So let us make a value associated with the node that compromises Avl tree property. Let us name that as alpha. Alpha is the node where Avl tree property is compromised. So on inserting a value into the right subtree of right child of alpha makes this compromise. So doing a rotation, so this rotation you are rotating towards left, so this rotation is called as LL rotation, making 6 as the root balances the tree. The mirror image will be something like, so I have a value 5 as the root. This is my existing tree. On inserting 2 here makes the balancing factor of 5 as 2. So this is my alpha. So now bringing 4 as the root and 2 as the left child of 4 and 5 as the right child of 4 balances this, and you are making a rotation towards right at 5. So this is RR rotation. These two rotations are otherwise called as single rotations. So now what if the scenario is something like, I have 6, 4 and I insert 5 here. So this scenario is, I'm inserting, so this is the node where balancing factor is compromised. So the balancing factor of 6 becomes 2. That is not possible in Avl tree. So now here insertion happens at right subtree of left child of alpha. So here we need to have a double rotation. Put in simple words, this rotation will enable 5 as the root, 4 here and 6 as the right child. So this rotation actually in turn, this has two steps. One step is making 5 over here, that is doing a left rotation, and then making a right rotation here at 5 to make at 6. So make 5 as the root. So this is LR rotation. The mirror image could be something like 6, 8, 7. So here inserting at the left subtree of right child of alpha. So again this is going to be RL rotation, makes 7 as the root and 6 as the right child, so left child, and 8 as the right child. So this lays the basic foundation for making rotations in Avl tree. So an example will help us to understand the concepts clearly. So this is the set of keys we have. To start with, I have an empty tree. Inserting 1 does not make any problem. Inserting 2 to the existing tree will not create any problem. Inserting 3 to the existing tree makes a compromise at the balancing factor of 1. So I am inserting 3, that is the right subtree of right child of alpha. So this is a single rotation case. Make a single rotation at 3. So that is a LL rotation at 1, sorry, makes 2 as the root, 1 as its left child and 3 as its right child. So to this existing tree, inserting 4 makes the tree looks like this. We just need to ensure that on inserting a new key, whether the balancing factor of any of the nodes in the tree is compromised. So here this is balancing factor 0, balancing factor -1, balancing factor 0, balancing factor -1. So no issues. So let us insert next value 5 into this existing tree. So inserting here will make the tree look like this: 3, 4, 5. So it is very trivial that the balancing factor of 3 is compromised. So we need to calculate the balancing factor from the leaf for betterment. So now what happens again? This looks like the trivial scenario what we had here. We need to perform a LL rotation at 3, making the tree look like, so this is LL at 3, making the tree look like this 2, this 1, 4 will be my root for this subtree, 3 will be the left child, and 5 will be the right child. So now this makes a balanced tree. So inserting 9, to this existing tree makes the tree like 2, 1, 4, 3, 5 and 9. Now the balancing factor of 9 is 0, 5 is -1, 3 is 0, 4 is -1, 1 is 0, and when it comes to 2, the balancing factor is 1 minus 3. This is -2. So we need to perform a rotation at 2. We need to identify what is the rotation that we need to perform. This is alpha. We have inserted into the right subtree of right child of alpha. Right? So again we need to make a LL rotation at 2, making the tree to look like this. So 4 becomes the root, 2 goes as its left child, in turn 1 goes as its left child, 5 and 9. What happens to my 3? 3 should be as the left child of 2. Now, so what is the existing tree? We have 4 as the root, 4 as the root, 2, 1, 3, 5, 9. So inserting 8 into this tree will insert 8 at this place. Now, do we have any node with a compromise in the balancing factor? Yes, it is 5. So what is the rotation we need to perform? We just need to identify what made the balancing factor of 5 to -2. Inserting into the left subtree of right child of alpha. So we need to go for a double rotation. We will be performing an RL rotation at 5, making, so this part is untouched, making 8 as the roots for this subtree. 5 becomes the left child and 9 becomes the right child. Now, what is the next element to insert? So now this makes the tree balanced. 7 is the next element to get inserted. So the current tree is 2, 1, 2, 3, 8, 5, 9. Inserting 7 will insert as the right child of 5. So inserting 7 makes any compromise in the balancing factor of any of the nodes? No. The next element to get inserted is 6. So this is the current tree. So inserting 6. So 2, 8, 1, 3, 5, 9, 7. Inserting 6 should insert 6 as the left child of 7. Now this makes a compromise at the balancing factor of 5, making it to -2. So here again we need to go for a double rotation, RL at 5, making the tree to look like 4 as the root. This left part is the same, right part 8 is the root, and here it makes 6 as the root for this subtree, 6 as the root for this subtree, and 5 as its left child and 7 as the right child. So this makes the tree balanced, and this is the AVL tree for the given set of elements. Thank you.